We now move to an example that illustrates the last point that we were trying to make and understand. And we have put up on the board an equation that reads d2y dx2 plus 6dy dx plus 13y is equal to 0. Now, straight away the auxiliary equation is nothing but m square plus 6m plus 13 is equal to 0. We can solve this equation by saying that this of course implies that m square plus 6m plus 9 is equal to minus 4. In other words, m plus 3 whole square is equal to minus 4, and that implies that m plus 3 is square root of minus 4, and that is plus or minus of 2i. So the values of m are minus 3 plus 2i and minus 3 minus 2i. So according to what we have just said, the solution is y is equal to e to the power of, this is the alpha and this is the beta, alpha plus I beta and alpha minus I beta. So comparing with what we have done before, our alpha becomes equal to minus 3 and beta is equal to alpha plus I beta, alpha minus I beta 2. So our solution, if I rub out this particular equation, the solution is y is equal to e to the power of alpha x, e to the power of minus 3x into cos beta x plus I sin beta x. So C1 cos 2x plus C2 sin 2x. This is the general solution of the equation that we have just written down. So with this, we are sort of home as regards the solution of second order differential equations with constant coefficients is concerned. Taken for granted that the equation is homogeneous, that means we have just got the general solution and no particular integral, which we will tackle later on. We now go ahead and take on our plate another category of equations, which is best described as follows: equations of first order but of higher degree. Now here we will allow terms that contain dy dx and higher powers of dy dx. In the equation itself, we will allow the presence of not only dy dx, so we write not only dy dx but also say dy dx to some power r. or evidently is more than 1. So we will allow the presence of dy dx whole squared terms, dy dx whole cube terms, and so on. So we will go through examples, but before that, let me state that this class of equations, which are categorized as equations of the first order but higher degree, there are 3 broad classifications to this generic type of these equations, and those are as follows. Three broad types. Namely, first, equations solvable for P, and P stands for dy dx. Equation solvable for P, that means we get P explicitly in terms of x and y. Secondly, equations solvable for y. And thirdly is equations solvable for x. So these are the 3 categories. In differential equation terminology, P stands for dy dx, and its neighbor Q actually stands for dx dy. That means Q is 1 by P whenever both P and Q exist, because these dy dx and dx dy, they are point by point phenomena, so both of them must exist. If 1 by P is not, this P is not 0, then Q is dx by dy. That's it. So we will take the first case and then tackle the other 2. To get a bit of more space, we rub out the entire board and write case 1, equations solvable for x. Equation solvable for P. Now, if that be the case, we write down the equation in whatever form and ultimately simplify it to the following. That means the equation can be factored as P minus F1 xy, P minus F2 xy into 2, P minus Fn xy is equal to 0. In other words, the original equation we assume is of the form, the equation form is P to the power of n minus capital P1 P to the power of n minus 1 plus capital P2 small p to the power of n minus 2 capital Pn into nothing is equal to 0. So these P1, P2, Pn, they are coefficients. Of course, they contain x and y. Each of them can contain either x alone or y alone or both x and y. So that is the equation. It is bereft, being a differential equation, it is bereft of any arbitrary constant. It can have constants but not arbitrary constants. So the small p, as I said earlier, is this p stands for dy dx, and pi, capital P's, are functions of x and y generally both. And we assume that these can be factored in such a way that we write the equation in a factor form. That means here we have factored it into n factors. So there are n factors here. Then these two are synchronous to each other. So it's a polynomial equation, it can be factored into n factors. That is a different question actually, because it's sometimes difficult to factor polynomials of degrees higher than 4, 5. So we'll have to see each equation and judge it by its merits and factor it accordingly. Now, if this be the case, then we can take solutions as follows. Supposing we start with this factor, P is equal to F1 xy. In other words, our dy dx is some function of x and y. Let us say that it throws out a solution. This particular one gives the solution y minus f1 xy plus c1 is equal to 0. So from here, because this is dy dx expressed in terms of xy, there are many cases, different cases. Not all of them are solvable, but assume that we can write a solution as y minus capital F1 xy plus c1. Because it is a solution, it must have a arbitrary constant. So if that be the case, if this particular solution can be evaluated, then for each factor we can have a solution like this. So the solution automatically will be the product of all such factors is equal to 0. So corresponding to the first factor, this was the solution. So we'll write that implies y minus f1 xy plus c1 is equal to 0 on the right hand side, is equal to 0 here. Okay. For the second factor, we get absolutely a similar term like this. So the solution is y minus f2 xy plus c2, that's equal to 0. And like that we go on till we write y minus f sub n xy plus cn is equal to 0. So each of these is a solution. So what we do is, instead of writing so many zeros, we just remove all of them and write the product as being equal to 0. Because each of them is equal to 0, so the product is equal to 0. This is the solution, but there is one problem, that in this solution we see n independent arbitrary constant, but the equation was of the first order. Nth degree fine, but first order. Hence, this solution will not be allowed unless we make C1, C2, Cn, C3, everything equal to one common C. So now we have this as the general solution with exactly one arbitrary constant, and that is C.